Let's get right to it. Engineering drawings are the universal language of making things. Without clear rules, your brilliant idea stays trapped in your head. Drawing standards are the grammar and dictionary of this language. Without them, chaos reigns. Imagine building a car with instructions in a language you don't know. Standards like ISO and ASME ensure everyone, everywhere, interprets drawings the same way. ISO is used globally. ASME dominates in the US. They're like dialects, similar, but with key differences. Understanding both is essential in today's global projects. A design might start in California, get built in Germany, and assembled in Mexico. If teams don't understand each other's standards, mistakes happen fast. This isn't just about avoiding errors, it's about building efficiently and safely. Standards are the foundation of modern manufacturing. They make sure your ideas become real, functional products. That's why they matter. Picture this. You design a part, send it to the shop, and get back a useless mirror image. The culprit? A simple misunderstanding of projection standards. Standards exist to eliminate ambiguity and prevent these costly mistakes. In engineering, ambiguity leads to errors. There's no room for guesswork. With thousands of parts made worldwide, only shared standards keep everything fitting together. ISO and ASME make global collaboration possible. They're more than rules. They're a pact between designer and builder. The designer promises clarity. The builder promises precision. This trust is the backbone of every successful project. It's how complex machines come together seamlessly. Without standards, manufacturing would be chaos. With them, we build with confidence. That's the magic of making things work. Here's the classic pitfall. Projection methods. ASME uses third-angle projection. Imagine your object in a glass box. Views are placed where you'd expect. Top above, right to the right. ISO uses first-angle projection. The object sits on paper, and views are unrolled. Top below, right to the left. Mix these up, and you get mirror image disasters. Drawings always show a symbol in the title block. The third angle, the circle is on the left. The first angle, the triangle is on the left. Always check this symbol before interpreting a drawing. Ignoring it is like ignoring a stop sign. Eventually, you'll crash. These projection methods are the most fundamental difference between ISO and ASME. Get it right, and your parts fit. Get it wrong, and you're in trouble. It's that simple. Learn to spot the symbol. Know which system you're using. That's how you avoid costly mistakes. Projection matters every time. Now, let's talk numbers, dimensioning and tolerancing. ASME uses unidirectional dimensioning. All numbers read from the bottom, clean and simple. ISO often uses aligned dimensioning. Numbers follow the dimension line, even if you have to tilt your head. Symbols differ too. ASME uses R for radius. ISO might just use a line. Countersinks, counterbores, and other features have subtle symbol differences. Tolerances, how much a part can vary, are handled differently as well. ASME might specify a general tolerance in the title block. ISO refers to a specific tolerance grade. These details matter in precision manufacturing. Misreading a symbol or tolerance can ruin a part. Always check which standard is being used. Know the differences, and you'll avoid confusion. Precision is everything. That's how you get parts that work. Even the paper size is standardized, and it matters. ASME uses inch-based sizes, A size, letter, B, C, D, and E, each one doubling the previous. ISO uses the metric A series, A0, A1, A2, A3, A4, each half the size of the previous, always the same aspect ratio. ISO system is elegant. Cut an A0 in half, you get two A1s and so on. This makes scaling and printing easy, no wasted space. ASME sizes don't scale as neatly. Mixing standards can cause printing headaches. An ISO drawing might not fit an ASME printer. In big projects, these small issues add up. Always check the sheet size before sharing or printing. It's a small detail, but it keeps projects running smoothly. Standardized sheets mean fewer surprises. It's all about making collaboration easier. Even the paper matters. Now for the advanced stuff. Geometric dimensioning and tolerancing, or GD&T. GD&T controls not just size, but form, orientation, and location. ASME Y14.5 and ISO 1101 are the main standards. The core symbols, flatness, position, runout, are mostly the same, but the details differ. ASME is self-contained. ISO splits rules across several documents. ASME's rule number 1 ties size limits to form. ISO requires explicit form tolerances. Some symbols and modifiers are unique to each system. These differences matter in high-precision industries, like aerospace or medical devices. The wrong interpretation can mean rejected parts or higher costs. GD&T experts are valuable because they're fluent in both systems. Always check which GD&T standard is used. Don't assume they're identical. Mastering both makes you a better engineer. Precision here is non-negotiable. So, which standard should you use? It depends. Geography is the biggest factor. US companies use ASME, European companies use ISO. Using the local standard minimizes confusion and leverages your team's expertise. For global projects, many companies adopt ISO for consistency across borders. Switching standards isn't easy. It takes training and time. Some companies use both ASME in the US, ISO elsewhere. The key is clarity. Always state the standard in the title block. Don't leave it to chance. Make your choice explicit. The right standard streamlines your project. The wrong one creates friction. Choose wisely and communicate clearly. Here's the bottom line. ISO and ASME aren't rivals. They're two ways to achieve the same goal. Clear engineering communication. In today's world, you need to understand both. Know your projection methods, dimensioning styles, sheet sizes, and GD&T rules. Always check the title block and projection symbol. Pay attention to notes. They're the rules of the game. Mastering both standards saves you from costly mistakes and makes you a better collaborator. The goal is shared understanding across the shop or across the world. By learning both, you're building bridges, not barriers. That's what engineering is all about. Be curious, be precise, and always check the details. The world builds together now. Draw it right, build it right. Go make something awesome.